No mystery there, huh? So what's going on? Okay, so what I'm going to do is I was asking Peyton earlier how was the other two videos for the last section. Was that satisfactory? Was that okay? Did it cover enough material for you ladies?
Yeah, I think I'm good.
Okay, because I tried to give you a lot of like places you could practice if you needed to, so you have that out there as well. Okay, so what we're going to do today is start similarity. So let me just get my iPad and I'll share the screen. So I have put everything on my iPad as a PDF so I can actually write on it this week, which is so exciting. That's great. Okay, so let me try the old screen share. I'm on an iPad. Okay, so I use this very busy cover sheet to kind of do like a preview of what's coming. So we're going to talk about similarity statements. There are ways of solving triangles, and the three ways really are law of sines, law of cosines. They work for any kind of triangles. And then you have the SOH CAH TOA method that works only for right triangles. So we're going to go over all of those. Then in the previous chapter, we talked about congruency. And we talked about like side, side angle, side, HL, all the different ways that you can prove congruency of triangles. Now we're going to prove similarity. So similarity is kind of the scale factor. So think about the relationship between a large Adirondack chair and a children's chair. So those are similar. They are the same general shape, but all the angles are different. So the sides are in proportion and the angles are identical. And there's three ways to prove that triangles are similar, and they're listed right here. So angle, side, similarity. So it's not exactly the same as the congruency, and side, similarity. So that's what's coming. Then there's some neat things. You generally learn that a Pythagorean theorem deals with a right triangle, but you can also figure out if it's not a right triangle using a modification of the Pythagorean theorem formula. And then these are a whole bunch of similar shapes right here. So it kind of goes with our theme. So that kind of starts us off. So here is the first similar polygon that I'm going to put up. So by definition, polygons are similar if their corresponding angles are congruent. So you have to have angles have to be congruent, and the corresponding sides are in proportion. So they don't have to be congruent, they have to be in the same proportion. So an example of that would be this triangle ABC and DEF. So important thing, this is a similarity statement. And usually that is a good guide to help you with your, to identify your similar parts. So we already know that if this is ABC and they're in the same orientation, so it's easy enough to look at the triangles, but if they're not in the same orientation, like if one is spun around, you want to rely upon the similarity statement. It makes life so much easier. So the bottom line is every angle has to match its corresponding angle. So you can see the little hash marks on A match the hash marks on D. And that's because they are both the first letter in the triangle. And the hash mark in B matches the hash mark in E because they're the second letter. And so on for C and F. So that you have to have. So if you're going to go ahead, you can list out your congruent angles. And the congruent angles are going to be, I can either use my triangle or use my similarity statement, but angle A is going to be congruent to angle D, and angle B is congruent to angle E, and angle C is congruent to angle F. So you want to use that angle symbol when you're talking about angles. And that equal side with the little tilde is a congruency symbol. So then if you want to figure out the proportional sides, this is where the similarity statement really, really helps. So if I make this a little bit bigger, and if I grab the first two letters, so AB is going to be in proportion to DE. So you can see this is AB and this is DE. So I can write that this way. So AB is in proportion to DE. Now these proportions are all going to be exactly equal. So then I'm going to grab a different color highlighter and I'll say BC. So BC is the next two letters. BC is going to be in proportion to EF. And then I would write that. So I have BC is in proportion to EF. And the last thing we have to have, grab the kind of the first and last. So that's going to be these two sides. And we can say that AC is in proportion to DF. So big things to stress if you ever get a chance to teach this. Notice that in all of the cases, my top numbers all went with the small triangle, and my bottom numbers all went with the big triangle. So you have to keep that order. And it doesn't matter whether you always go big to little or little to big, as long as you are consistent. So what you're going to find, many times they'll give you the scale factor by the way that the triangles are presenting themselves. So you have the small one first, and then you have the big one. So most likely in a problem, they're going to tell you the scale factor is small to big. So when you figure out the scale factor, it should work every single time. So AB was 6, and DE was 9, and BC was 4, and EF was 6, and then AC was 3, and DF is 4.5. So these fractions all are equivalent. Now, sometimes it's hard to see if they're equivalent because they look so different. But what's nice is if you put them in your calculator, you will get the same exact decimal value. And sometimes that is the quickest way to check it. Because right now I can see if I doubled the top and bottom for the last fraction, I would get 6/9. Then if I divided 6/9 by 2, yeah, I can't even do that. Okay, so if I reduce this down to 3 to 2/3 and double that, I would get 4/6. But you have to do a little manipulation to do that. So sometimes kids will say, well, I don't think 6/9 and 4/6 looks very similar. So you can play around with reducing the fractions, but you can also say, okay, let's put them in our calculators and see if they are the same exact decimals. Because if they are, then you know you're good to go. You always want to check all three as well, just to be on the safe side, to make sure that you haven't missed something about this shape. So you can prove you have this congruency a number of ways here, because you have all the components of the triangles. But you can prove it if you have only partial congruence or partial similarity, and we'll do that in the next two examples. So everything okay so far? I'm throwing a lot of color out there, but similarity is good. It's a nice little feature, and I think because people are used to, like, doll houses, having miniature furniture, kids have a lot of practical applications of what that could mean, which is nice because you don't really have that with some other parts of math. So if we look at the next page, they tell us that if we only have two angles the same, so if two triangles have two pairs of corresponding angles that are congruent, then we can say the triangles are similar. Okay, so in this situation, we do indeed have the two angles. So once you see this, you can prove congruency by AA. Now, notice that these guys are not in the same orientation. So if you're going to write a similarity statement, which they frequently will ask you to do, you've got to look at your angles. And so what I tend to tell the kids is start with the lowest hash mark. And I'm going to call the first one triangle BAC. I have markings for B and for A and nothing for C. So that's going to be similar. Okay, so that's the similar statement. The triangles themselves are similar. The angles are congruent and the sides are in proportion. So you've got three different symbols going on. So that was BAC was the first hash mark, the second, and then the no hash mark. And then this is ZYX. And I'm going to put a little triangle symbol in front of that too. So that's telling me that this is my similarity statement. Now, sometimes the kids will say, well, how come I can, if I only have two, don't I have to have the other one? Well, if you remind them that there's 180 degrees in every triangle, and you know two of the three angles, don't you really know the third angle as well? So there's no need to have that other angle marked. It is good to the way it is. Okay, so once you have your similarity statement, then you want to have them practice setting up your angles. And in this situation, when the triangles have different orientations, you definitely want to have the kids focus on your similarity statement. They are much more successful if they do that, if they keep trying to like switch things around in their head. So your angles that are congruent would be angle B is congruent to angle Z, and angle A is congruent to angle Y, and then angle C is congruent to angle X. Okay, so you see you have a different kind of relationship there. Between the angles, you have congruency. Between the triangles, you have similarity. And between the sides, you're going to have equal proportions. Okay, so now it's really important to use the similarity statement when you try to figure out your sides, because if you keep switching the orientation, there's a good chance you're going to mess up. So you would do the first two letters to the first two letters, and now you have a different symbol. These are equal. And then you have the second two letters to the second two letters, and then the first and last to the first and last. Okay, and if I had numbers in here, I could verify it, but I can establish the relationship once I see I have two equal angles. So this is one of the similarity theorems. Okay, so then there are only two other ones. So the other one is side angle side. Now this is side angle side similarity as opposed to side angle side congruency. So if two triangles have two pairs of corresponding sides in the same ratio, and if the included angles determined by the pair of sides are congruent, then the triangles are similar. Okay, so that's a mouthful. So what we say is you need to have a sandwich situation. So I have an angle, I have a side, I have an angle, I have a side. The angle is kind of the jelly in the sandwich. And that's what you need to prove you have similarity. So if we're proving congruency, the sides would be equal. But if you're proving that you have similarity, the angles are equal and the sides are in proportion. So then you say, well, which sides are in proportion? Well, pick the smallest side first. So that's AB in the triangle to the left. Then pick the smallest side in the other triangle. So this proportion should hold. So then pick the biggest side, which is BC, and then you're going to pick the biggest side for the other, which is FE. Okay, so let's check to see if they're in proportion. I can already see that my angles are exactly equal, so that's good. So then my proportion is going to be AB was 12, so 12 is 2, and then FD was 8, just like BC was 24 is 2, and FE is 16. And I can see that there's a multiplier of 2. So what they frequently ask you here is they want to know what is the scale factor. So the scale factor is going to be the reduced proportion. it is most likely, it's most often, I should say, represented as a fraction. So you would take your 12 over 8 and say, okay, I can reduce that. So I can reduce that to 4 goes into 12 3 times, 4 goes into 8 2 times. So my scale factor is best represented as 3/2. Okay, so then you could do other things with this. You can have them based on this information. They're going to write a similarity statement. So how would you do that? So you're going to follow the same path on both triangles. So if you come down the small side towards the angle and then up the bigger side, write down the letters that you come across. So this is triangle ABC is similar. Oops, I want to do similar. Is similar. Okay, so do the same thing. Go down the small side. So that's DF. And then up the bigger side. And that's E. So that's how I get my similarity statement. So we can say that by similarity or by SAS similarity, I can state that those two triangles are similar. I could tell you the sides that are in proportion, and I can also tell you the angles that will be equivalent or equal, and I can tell you the scale factor. Okay, and then the last way to prove it is if you have side, side, side similarity. Again, side, side, side similarity is not the same as side, side, side congruence. So what you're going to do here is you're going to make ratios of the small to small, big, medium to medium, and big to big. Okay, it's like the Three Little Bears. That's how you're going to set things up and see if they're all the same. And if they are, then you know you have side, side, side similarity. So you would say, okay, the smallest side on the left triangle is going to be AC. So I'm going to do the numbers and see if it works out. So AC is the smallest, 10 is the smallest on the right triangle. The next one is going to be 21, and then the next size on the right triangle is going to be 15. And then the last one is going to be 28, and then I'm going to have 20. So you can play around with reducing these. So if I put, let's see, this is even, so that's going to be 7/5. Okay, so this 3 goes into this 7 times, 7/5 again. And can I get 7/5? I can if I put 4 into the numerator and the denominator. And I can't reduce that any further. So 7/5 will be my scale factor. And then in order to get a similarity statement, you've got to be careful because you have no angles here. So if you went from the smallest to the medium, that would be triangle CAB, and then do the same thing. Go from the smallest to the medium, and that's going to be DEF. And those are the triangles that are similar. That's your similarity statement. Once you have your similarity statement, then you know that angle C equals angle D, A equals angle E, and B equals angle F. You can kind of figure all that stuff out. Okay, so that's all the similarity pieces. So most geometry classes cover this pretty extensively. And where the kids struggle is, seeing what are equivalent fractions. That's a whole nother little unit there, because you've got the fractions to work with and to reduce them and to, put them into decimal form. So that's a struggle area. A lot of them will struggle with getting the similarity statements, especially if you switch the orientation of the triangle. So if you ever teach this, you probably would start out not switching the orientation and then switch it and show them the importance of the similarity statement. And it really does help them to get the things correct. Okay, so anything on those? So then we're going to kind of play around with a little bit of this. We're going to do just one little problem in here. And then what I have some neat applications that are really fun. That deal with shadows and stuff. So you can do real life applications of this pretty easily. So it's a nice topic. So the next slide for this is practicing with similarities. So that kind of brings us to some of the parallel line stuff that we studied in the previous chapter. So notice what they did. They have a triangle inside a triangle. And a lot of times it's really helpful to redraw this so that you have the small triangle here. And this is X and this is 6. And then I have the bigger triangle here. And this is where you've got to be careful, because the left side is going to be X plus 1, and the right side is going to be 8. And I don't know the bottom. So it says solve for the missing side using similarity. So first figure out why the inside triangle and the larger triangle are similar. So if we try to figure that out, we're going to figure out, well, what can I do? Well, I don't have enough sides to work with. And then you think, well, I really don't have enough angles either, but you really do, because look what happens. They both share this top angle. So that means right away that that top angle and that top angle are equal. So then you think, okay, but now I'm stuck because I don't have any other equal angles, but you actually do kind of hide in there. If you look at the parallel lines, and let's say we extend these parallel lines, and then all of a sudden we can view this part of the triangle as a transversal. And now what happens is all of a sudden we have corresponding angles, and corresponding angles are always equal. So right away, and don't make them the same hashtags, because you don't want to force angles to be equal that you don't know whether or not they are. So now I have angle similarity, and now I know I'm good to go. So with angle similarity, what we're going to do is figure out how we're going to find the missing side. So if you take, because now I know my orientations are good, so I can say X is to X plus 1, just like 6 is not to 2, but to 8. So the kids tend to like to look back at the original triangle, and they'll end up kind of messing up the proportions. So that's why if you have them redraw it, it's always helpful. But then use the original triangle to show them why you can set 2 angles equal. Remember, you only need 2 angles equal, and then you're good to go. And we could have picked the other pair of angles because they're going to be also equal, because they'll be corresponding angles as well. So once we have this, now you have kind of a nice little algebra problem. So if you have fraction equal to fraction, the best way to handle this, I think, is to do the cross products. So I tend to, reinforce that by saying that product equals this product. With the product of the means equal the product of the extremes in terms of technicalities. So here's another example of a time to stress distribution. If you have them right like that initially, there's a better chance they're going to probably get this good, or this, done correctly. So this is 6x plus 6 equals 8x. Now you have a 2-step problem. And that's going to be 6 equals 2x, divide by 2, divide by 2. I'm getting x equals 3. So I don't know exactly what the proportions are yet, but I can figure out some x's now. So if x is 3, so I'm going to replace this with my 3, and I can replace it here as well. Now I can replace this as 4. Okay, so now we can kind of play around a little bit. So what I'm seeing is that we have 3, 6, and 4, and 8. And so what I set up, when I look at where my cross products was, I can easily see that 3 is to 4, just like 6 is to 8. And so I can see that they are both equivalent fractions. So in that case, my scale factor equals 3/4. Okay, so I've got my two proportions set up, and I'm good to go. Now I'm just thinking about this. So it says we want to figure out the missing side, but I'm trying to figure out how you would find the missing side. I can tell you a range of sides, but I don't think I can find the missing side given what we know at this point. Am I missing something? Because I know, for example, by knowing about triangles, if I have a 3 and a 6, then I know, so this side will be, so less than 9 and greater than 3. So I do know that. And then this other side here will be less than 12, but greater than 4. So maybe you can just play around and figure out the scale factor. So that would be one investigative way to figure that out. Because I need a factor of 3 to 4. So then the question is it going to be a whole number? So I would have 4, 5, 6, 7, or 8 here, and I would have 5 through 12 here. So I think perhaps you could play around and find the one that's missing. But that's work for another day. So that would be interesting. So I think if I gave this kind of problem, I'd be very happy if they figured out what x is, and if they figured out the scale factor, and then if I put letters on things, if they can then write for me the similarity statement. I think that's how I would handle that. So then there are really interesting applications that have to do with the shadow of the sun and all of that. And they're all tied to the AA. So I want to show you one here, and then we can work on some of them because I have some worksheets that I put up. So here's your situation. It says a girl that's 160 centimeters tall stands 360 away from a lamppost at night. Her shadow, so here's where the girl is. So this is all the girl pieces. So we'll make that pink. Okay, this is all the girl stuff. Here she is. Here's her shadow. So then the lamppost will make green. So here's the lamppost. So her shadow from the light is 90 centimeters long. How high is the lamppost? Well, the lamppost shadow is all of this. So you're going to set this up as a proportion. So what you can say, and now the question is, why can you say that? Well, there's a couple of things you want to think about. So you have this shadow coming down. So a lot of times they'll say, okay, this is the sun, and the shadow's hitting at the same angle. So therefore, this angle has to equal that angle. So you've got two angles in common there. The other thing they assume, the lamppost is at a 90-degree angle, and your little girl, is standing up very straight. But then you have a third angle that you can also use because look, this toe angle over here, and I'll put 2 hash marks, that's common to both triangles. So you can use AA and you can pick any 2 of the 3 angles in order to prove it. So now I know that this is a candidate for similarity. So far what I know is that the height of the girl is in proportion to the height of the lamp. And then her shadow, which is 90, is in proportion to the shadow of the lamp, which you have to make sure that you take the 360 and add the 90 to it, so you get 450. So those are your proportions. And sometimes you've got to go over this a couple of times. But then once they kind of start seeing, oh yeah, I've got the shadow, the lamp, really, that shadow merges with the girl shadow. That's kind of a concept to understand. Then you get your proportions and you're going to do your cross products. And I believe what I got was that x equaled 800 and that my scale factor, small to big, was 1/5. So that's how you do those shadow problems. So at this point, I have a document that's up on Google Classroom, and it's called Applications. So it looks like this, but it's called Applications Using Similar Triangles. So I was going to show you that so you can see that there are other kind of very neat problems. So let me get out of this because I have this someplace else also. So let me just get out of that. And then I'm going to go back into Notability. So here is the shadow problems. So I thought, why don't you guys try to work through one yourselves? So let me pick up a good one. Okay, so you've got these neat ones that are kind of similar to what we just did. The difference is that the clock tower and the stick are not sharing a shadow. So this is probably a better one to start off with kids because you don't have to add up the two shadows to get the shadow of the taller item. Here's another one when the two figures are looking at each other. So you've got a lamppost and then you've got a man. And so you kind of have a little different thing going on there. And this is kind of tricky because you've got this right angle here, but the other angle they say you can prove is going to be equal are the toe angles. And they say these angles are congruent because light reflects off a mirror at the same angle that it arrives at. So the thing is that they introduced this little mirror. So it's kind of a contrived problem, but it's kind of an interesting way to think about it. So then you also have these other problems that are kind of neat. And they, there were problems also, so it's a little bit more engaging. Here you have the zebra at the zoo. So we've got all kinds of problems here. Here is, why don't we do this one? So why don't you guys do this one and I will just be here. So you can do it any way you want to do it. I think, can you see it here? Know that you have this whole document too that's up if you want to practice this or use it for whatever you wanted to use it for. So I would say the first thing that you'd want to do is label things. So you can label it. So why don't I do this? Can I do this? Why don't you do a little sketch of this? And then what I'll do is I'll put you in breakout rooms so you can talk without me having to be right there and see what kind of answers you get. And then I'll do mine and then we'll get back together again. So I'm just going to label this in the meantime. Okay, so you have to be careful. The base of a tree is 20 feet from the bottom of a flagpole. So that means this is 20. Okay, so I think that's the way I want to set that one up. So that wording is tough because you've got to put things in the right spot. Does everybody have a little bit of a picture of this? Okay, so why don't I stop sharing and I'll put you into breakout rooms. And since I only have 3 of you, I'll put you into one breakout room. There we go. And I can open your rooms and now you can hop in the breakout room and you can talk all about similarity. And then I'll pull you back in just a minute and we'll compare our answers. Peyton, you came back, but I'm waiting for the other ladies too.
Yeah, I think it popped up for them too, but I think they're coming.
Yeah.
It says all here.
Oh, there you
I'm
go.
here.
Oh, yeah.
Oh, everyone's here. Yay. Okay. So what did we think? What did you get for the height of the tree?
32.
Yep. I agree. So this is a more difficult one just because of the wording. So you've got to be careful about that, but otherwise it's kind of a neat problem. And these are things too that, you know, if life is normal, you can take the kids outside and see if you can do some measuring with their shadows, you know, and trees, and it's kind of a fun activity. So anyway, so you have more of these here. If you want to use them for anything, if you feel that you want more practice yourself, there's all kinds of things there for you. So that's one activity. So then we go back to my notes. What the author tells us is that this similarity idea, if you have similar triangles, their altitudes will also be in the same proportion. So that's kind of nice, you know, and then altitude is defined as the distance, the vertical distance from a vertex to at a 90-degree angle to the side opposite it. So that's an altitude. And you can see by this that for acute triangles, altitudes are inside. For right angles, they're on the edge, and for obtuse, they are outside. So you can figure out, if you know that two triangles are in proportion, you can then figure out other measurements without having to do any other kind of math. You can just use that scale factor. And I think I have a little video embedded in here. So if two triangles are similar, then the altitudes would be in the same ratio. Just to fly past this for a second, because for some reason, I think the author went back to this later. Your area and your perimeter are also going to have a relationship. So if the perimeter and of two triangles that are in the same proportion will also be in the same proportion, but the area will not be. They'll be in the same squared proportion. And the volume, if you continue it out, will be in the same cubed proportion. So you can kind of do neat things with that. But this they kind of revisited again in 3.4. And I thought I would just mention it because it's kind of what we're doing right this minute. So let me go back and we will see that slide again. But the next thing that we have on tap here is the Pythagorean Theorem. So there is a nice activity in here as well called Discovering the Pythagorean Theorem. And that involves a lot of cutting, and you kind of get to see the proportions. So I'm going to let that for you. If you ever find a need or a time that you can use that in a class or want to just have a fun activity, I did the whole packet, and that's all posted for you. So Pythagorean Theorem, the key thing is there is a proportion between the legs and the hypotenuse. So the key thing, and this is the key thing that the kids always kind of forget, is that this hypotenuse is always directly across from the right angle. So usually I will spend a lot of time drawing these little arrows, even for like my sophomores, because just to, refresh, okay, where is it? Because you change the orientation of the triangle and they get very confused about that. So it's nice to give them like a little bit of a roadmap. So, and if you set up your proportions, I don't try to tie it so much to these letters, because if the letters change, they have nothing to hang their hat on. So what I tend to tell them is that a good way to think about Pythagorean theorem is leg squared plus leg squared equals hypotenuse squared. And that's always how it works. So that is by far the safest thing, because then they don't have to worry about, well, but my C is in the wrong spot. There is no wrong spot. There is no right spot. So try not to teach it tying it to the letters. The traditional letters are here. And what I'm going to tell you is that the C, the little c is a side. It's across from the big C, which is an angle. The little a is a side. It's across from the big A, which is an angle. And the little b is a side, and it's across from the big B, which is an angle. So that is the way that that math people use their letters on triangles. The capital letters are always the vertices, the angles, and the small letter opposite it is always going to be a side. Okay, so that pairing is very helpful for them to understand. But then in terms of the formula itself, it's nice to have them know that it's leg squared plus leg squared equals hypotenuse squared. And it's not leg plus leg equals hypotenuse, which they tend to sometimes want to do. Okay, so that's the Pythagorean theorem. And as I said, there's a little discovery activity right here. And here's where I got it, but you have an electronic copy as well. So the converse of the Pythagorean theorem comes in very, very handy. So if you always set it up in theory that you have a squared plus b squared equals c squared, this is what ends up happening. When you have an equality, you have a right angle. Okay? If you have a squared plus b squared, so the legs squared, that sum is greater than the biggest side squared, because in this case, it's not going to be a right triangle, but you're always going to have the c side, if you would, in the formula, be the biggest side. So if you have a situation where the two smaller sides, each squared, is greater than the largest side squared, then you know that your angle in question, which is the biggest angle, which is the angle that you're kind of testing, is going to be an acute angle. So you have an acute triangle. If, on the other hand, you take the two smallest sides and you square each one, and you find that's less than the largest side squared, then that angle C that's across from that little side C is going to be obtuse. So there's a little trick with this once you kind of understand the concept. And the trick is this. If this arrow is pointing towards the C, if you think about the inequality being an arrow, then your triangle is acute because there's a C right there. If this angle, which is the less than symbol, is pointing towards the B, then your triangle in question is obtuse. And that's kind of a nice way to have the kids remember that. So an example of this would be if my sides were 3, 4, and 5. 3 squared plus 4 squared gives me 5 squared. That equals, so I know that my angle C is going to be a right angle. If instead I try to do a 5, 5, 6, 5 squared plus 5 squared, so that's 25 plus 25 is 50. That's greater than 36, which is 6 squared. And therefore, this is going to be an acute triangle. And the last one, I tried out 3, 4, and 7. Take the two smallest ones and square them first. So that's 9 plus 16 is 25. And 25 is less than 49, and therefore it's obtuse. So if you always think of it in the order of A, B, C, you can do that little trick. So then there are Pythagorean triples that you probably are very familiar with. Most people are familiar with the top line here. So those triples will always be right triangles because they will always follow this progression, where the legs squared equals the sum of the legs squared equal the hypotenuse squared. It's nice if you recognize these because it saves you some math work sometimes, because you can just see, oh, it's a right triangle. I know that one leg is 9, the other one is 40. Boom, it's 41 because that's a triple I happen to know. So anyway, those are the triples. That's how it's set up. So when explaining this, when your triangle is not a right triangle, your A and your B are the two smaller sides, and your C is always going to be the biggest side, because you're not going to call it a hypotenuse then, because that word only goes with right triangles. Okay, so that's a neat little thing to know. So then this brings us on to a pretty big topic called the trig. And this is just right angle trig. So I don't know where you all are with right angle trig. How are you with SOH CAH TOA? Is that a friendly thing? Is it something that you kind of remember, but you don't do a whole lot with, which I would expect. So SOH CAH TOA. SOH CAH TOA, I always tell the kids it's a tropical paradise with a lot of right triangles. So you kind of make it something exciting, you know? So the way you write SOH CAH TOA is going to help the kids figure out what it is. So these little, yellow and red and blue triangles are oh so pretty, but that doesn't do a lot to help me know what it means. So I tend to do this. I tend to say sine is opposite over hypotenuse. Okay, so I have so, cosine is adjacent over hypotenuse, and then tan is opposite over adjacent. And then you can even, if you wanted to, put these little equal signs in there, because that's how you do the ratios. And the ratios are going to let you get missing values. So you're going to you can only use SOH CAH TOA when you are in a right triangle situation. You can't use it for any other triangle. So that has to be a right triangle. So if you see a right triangle, a right angle, think SOH CAH TOA. We're going to only work in degrees. You can do trig in radians as well. And when people get to pre-calc and you're using a unit circle, it is infinitely easier to have things in radians. And eventually the kids believe you. At first they think, no, lady, there's no way this is easier in radians. But it really is, because you can find reference angles. But we're not going to get that far. So in terms of what we're going to work on, we're going to do the trig in degrees. And so I'll show you how this works. So let's say we take a traditional 3, 4, 5 triangle. So I'm going to make this side 3, this side 4, and this side 5. So I have no angles in there. I only have sides. So I can use the 3, 4, 5 features to figure out an angle. And this is how I would do it. So let's do this. We're going to work with this angle over here, right here. Okay, and we're going to figure out what the sine of alpha is. So from alpha's perspective, the opposite is here. So it's going to be 3. And the hypotenuse is always across from the right angle. So this is 3 over 5. So the sine of alpha equals 3/5. And you think, well, that's just wonderful. What does that do for me? Well, if you use inverse trig, you can get the angle. So this is what we're going to do. I know that the sine of alpha, and I think this is gamma, but we're going to call it alpha, equals 3/5. So look what happens. The angle in question is going to equal sine to the -1, that's called inverse, of 3/5. So in my calculator, I'm going to say second sine, I'm going to put in 3/5, 3 divided by 5, and I'm going to find out that that angle is 36.9. So by doing this, I can find that my angle is 36.9 degrees. So I used inverse trig. When you look for angles, you use inverse trig. When you look for sides, you use straight up trig. And I have a practice sheet for this too, but I just wanted to go over it generally. So the 3 main trig relationships are usually the sine, cosine, and tan. So you want to memorize the SOH CAH TOA, and really it's SOH CAH TOA, because don't have another O there, because that's going to mess you up. So it's SOH CAH TOA. Then you have reciprocal functions. So the reciprocal functions are these. Okay, so if you take the sine fraction and you flip it over, you get cosecant. Okay, so CSE is cosecant, and cosecant is the reciprocal or the flipped upside down relationship of sine. If you take cosine, which is adjacent over hypotenuse, and flip that over, you get secant. So SEC is secant. If you take tan, which is opposite over adjacent, and flip that over, you get cotan. So it's not cot, it's a cotan. Or cotangent, I guess is probably even more specific. Okay, so that's how that works. So depending on where you put your angle, what you call opposite and what you call adjacent will change. But what never changes is your hypotenuse. That's always going to be forever and ever the same. Okay, so that's kind of a very, very big topic. So let's look at the handout I have for that. And I got it here. I don't know if any of you have licenses for CUDA software, but you can get free things there. So if you just type in CUDA, it'll take you to the CUDA software site, and then you can get free worksheets with their answer keys that are for different grade levels. And they have them for high school, they have them for grade school. So that's a great site. And I went there and I got the following activity. So let me come out of here and I'll show you what, well, I got, let me get out of there. And it is my SOH CAH TOA problems. So you can see it's CUDA software, and this is an Algebra 2 concept. Many times though, they will put right angle trig in geometry. In fact, that's where it should always start. And then maybe they do more things with it when they get to Algebra 2, but it really is a geometry topic. So why don't we try a couple of these? If you're going to find the measure of each angle indicated. So why don't I set up the first one? Because you have lots of ways to do this. So here is my angle. So I look at my angle and I say, well, what do I have? So I'm going to do my SOH CAH TOA here. Because I have to figure out what's the most efficient way to solve for this angle. So from that angle's perspective, I have the adjacent, which is 13. Okay, so that's adjacent, that's adjacent. Then I have the hypotenuse, which is 12. Hypotenuse, hypotenuse. Which one is the winner? The one that has 2 check marks is what I'm going to use. Okay, so I'm going to say now, from that angle's perspective, the cosine of theta equals adjacent, and I take that back, equals adjacent is 12, because look where the right angle is. It's equals adjacent over hypotenuse. Okay, so that's my relationship to get my angle. Theta equals cosine -1 of 12 over 13. So I would say second cosine -1 and then 12 divided by 13, and I get an angle of 22.6 degrees. So in this case, theta equals 26.2 degrees. So have you done this before? Is this familiar?
I did it, but like in high school.
Okay, and Claire is more familiar to you? It's not familiar. Okay, and Regina, you do know this.
Yeah, it's been a little while since I've done it though too.
Okay, all right. So you need to have some kind of calculator that will do it for you. So you need to have a calculator that has sine, cosine, and tan. And like I have a TI-84. And when you hit the second feature, that's when you get the trig functions to the -1 power.
They have sine, cosine, and tan on just like an iPhone calculator now.
Okay, perfect. So as long as you can get it, you're good to go. They don't tend to, I mean, I've never seen the reciprocal functions on it. So you would have to always use sine, cosine, and tan.
They have like sine H, which I don't know what that
Sine
is.
H.
And then like cosine H and tangent H.
Is that what they write instead of tan to the -1?
Maybe.
Because do you see sine to the -1?
No.
So
Then put that in.
I just found it on the iPhone calculator.
Okay.
So when I press, like, if you flip it sideways and then press the second button, they have the sign with a -1 and stuff like that, and then below it's the one with the H.
Yeah, so I know what the H is.
Oh yeah, so if you click the second, then it does give you the -1. I don't know what the H is.
Yeah.
Yeah, me either.
Okay, so on the cell phones, you're going to click the second button to allow you to go to the top of the keypad.
I wonder if those ones are like the reciprocal, like the cosecant, secant, and I wonder if that's what they might be.
Yeah, I wonder. I'll have to play around with it because I did put one on my, here it is, calculate 84.
Does anybody know how to do fractions on an iPhone?
You know, I don't think we couldn't find that ND key because you would say alpha y equals. Oh, there it is. Okay, so go to alpha and then y equals, and you see how it says ND? It says fraction, function, matrix. So
I
then
don't see any of that on the iPhone calculator.
yeah, I'm on my iPhone. It looks like my regular calculator, but it's my iPhone. So it's my cameras. So what I'm doing is, do you have a green alpha key?
No.
Oh, you know what? Download the TI-84. It's free. It's an app. That's what you want. It's pink. It says calculate 84. But it looks like my TI-84. So I think if you go into the App Store and go to TI-84, I believe you can download that for free. Let me just look there myself, because I did that with a class a couple of years ago. Okay, so we're going to say TI-84. Yeah, TI-84 plus calculator free. So yeah, get the TI-84 plus. And MAT may just be even the regular TI-84. They will all allow you to do the fractions, which is really key. And then I'll tell you how to do it. Yeah, because I don't have any of those H things. I just have my regular TI-84 calculator. And that's where you can also go second square root. Oh, and I have a great idea. Let me try to mirror my cell phone. So I'm going to stop sharing here. And then if I try to mirror this cell phone instead of my iPad. Yep, it did it. Okay, so this is my calculator on my phone. Okay, so if I want to do fractions, what I would do is I would say alpha and then y equals. And there's Noah giving me his homework. So, and you see you get fraction and you get n over d. So then I just hit enter. And then here I can type in 1. Oh, yeah, I type it on my phone. 1 bring your arrow down, and you can bring 3. And now I have a fraction. So it is alpha y equals. That'll do that. And then here's where your inverse trig is. So here's your normal trig, sine, cosine, and tan right here. When you want to access these keys here, what you're going to do is you're going to say second and then hit the key, and it'll come up sine to the -1. And then you can find the angles that we're looking for. The square root key is here. So you would hit second and then x squared, and that will give you square root. So when you're trying to solve a Pythagorean theorem problem, that's how you would do it on your cell phone.
Okay, so when I do cosine -1 and then put in the fraction box 12/13, I get 0.39.
So, okay, so let's try that again. So tell me what your fraction is. So you have cosine.
Yeah, cosine to the -1 times 12/13.
Okay, so let me try this on my phone. So I'm going to clear this. I'm going to say second cosine -1, and then I'm just going to do this, 12 divided by 13, and you have to make sure that it's in the parentheses. And then if I hit enter, I'm getting that. So let's go into mode, because we're in radians. So go to mode, and you see that we're in radians. So I want to go into degrees. Okay, so I'm going to say second quit, get out of there. And I'm going to say, if I say second enter, it'll repeat it for me. And then I'm going to say enter, and it didn't hold. Let me see if I can make sure it holds. So if I went to second mode, so I have to go to mode. Yeah, I don't think it held, although it should. Oh, yeah. When you do it, hit enter and it'll turn pink. And the other one, the black one's gone away now. So now they go back in there. Second quit. Second quit. With my quit. Second quit. Okay.
Okay, so I got 22.6 that time. I had it in radian.
Yep, that's good. You're good. So if I go second entry and do that, 22.6. Okay. So does that work? So
yes, thank you.
How are you with the setup? So do you see how I'm selecting whether I'm using tan, cosine, or sine? Because that's usually the more challenging piece of it. So why don't we try 1 or 2 more of those just to know that we're setting it up correctly. So you have your phone. So let me stop sharing my phone, and I will start sharing my iPad again. Okay, so let's do another one and see what the setup's going to be. So here, your delta is over here. Okay, so look at the SOH CAH TOA, and what I'm gonna talk out loud one more time. From this angle's perspective, I have the opposite and I have the adjacent. If I have opposite and adjacent, I'm going to use tan this time. So I'm going to say the tan of delta equals opposite over adjacent. And I think that's a 12. Yeah, I think it's a 12. Okay, so then when I want the angle, I'm going to say theta equals tan to the -1 of 4/12. So on my calculator.
This doesn't make much of a difference. I pulled it up as well, like on a separate sheet. I see 13 though on the.
Oh, thank you. Okay, so this is a 13. We'll make that a 13. And then I'm going to go back to my calculator. So I'm going to say second tan to the -1 of 4 divided by 13. And I'm getting 17.1. This is 17.1 degrees. So what the question that you want to ask yourself is from the angle's perspective. From this angle's perspective, what do I have? And know that as they change the orientation, you can always draw yourself down and get your right angle. Yeah, I've got a hard copy of this that I can grab, so I'm not guessing what the numbers are. Okay, so number 3, this is a 6, and that's a 9. So why don't you try to do that? From that angle's perspective, what do I have? So what do you think, Peyton? From that angle's perspective here for number 3, what numbers have I been given?
So from that angle, you have the 9 would be the opposite, right?
No, the 9 is always going to be the hypotenuse because it's
Oh, the hypotenuse. Okay, see, I was thinking opposite and adjacent, not the okay. So then
the hypotenuse, and then so I don't have anything across the street. Okay, that's going to be the opposite. But I do have a side that's touching. The side that's touching, that's not the hypotenuse, is the adjacent. It's like the townhouse, you know, it's touching. So since I have hypotenuse and I have adjacent hypotenuse, it's going to be cosine.
Mm-hmm.
So the cosine of theta equals, and its adjacent comes first, that's the smaller of the two, over 9. So therefore theta equals cosine -1 of 6 over 9. And that should be getting you 48.2 degrees if you round to the nearest 10th. Okay, so that's the angle part of it. For the angle, whenever you want an angle, you are always going to use inverse trig. Okay, because if you don't, what you're going to end up getting, so if you just type in the cosine of 6 divided by 9, you're getting 1, basically. And so you get a really small number. And as long as your mode is correct, that should tip you off that you didn't use the inverse. Okay, so we have these we can practice. Those are all about finding the measure of the angle. But you also use SOH CAH TOA to find the side. So let's go ahead and do some of those too, so you have both practices. So on the same document, on further down the page, it says find the measure of each side indicated and round to the nearest 10th. So this angle up here is 37. So I'll make this big and I'll write in what they are. This is 37. This is 11. This is X. And this is your right angle. Okay, so so it's always good practice when we first start doing this to always have this handy. So you always talk about from this angle's perspective. From this angle's perspective, and this is the hypotenuse, I have the adjacent, that's the townhouse. So I have the adjacent, and I need the hypotenuse. So the winner is cosine. So I'm going to say the cosine of 37 degrees equals, so adjacent is 11 over X. Okay, so you're just going to use straight up trig, no inverses. So envision this over 1 so that you can justify in your head doing cross products. So this is X times the cosine of 37 equals 11. And so I want to get X by itself, divide both sides by the cosine of 37. And what I'm going to find is X equals 11 over the cosine of 37. So, and you just 11 divided by cosine. When cosine comes up, you're going to get an open paren. Put your angle in the open paren and then make sure you close the paren. So the hypotenuse is going to equal 13.8. And that's bigger than 11. So that's consistent with my reasoning. Now, a lot of times they'll say to you, I'd like you to solve the triangle completely. So let's try to solve this one completely. You have a 90-degree angle. That's what this box indicates. There are 180 degrees in a triangle. So you're going to say 180 minus the 90 you have, minus the 37 they gave you, and this other angle should be 53 degrees. Okay, now you need the other side. You have some options. You can use SOH CAH TOA, no problem there, or you can do Pythagorean Theorem. Either way, you'll get the same answer. So what if I want to do Pythagorean Theorem? I would say leg squared plus leg squared equals hypotenuse squared. So my y squared is going to end up being 13.8 squared minus 11 squared. So I'm going to take the square root of the difference of those squared terms. And I'm getting that y equals 8.3. So this is 8.3. Now notice what's happening. The side opposite the largest angle is the largest side. The side opposite the smallest angle is the smallest side. And the mama bear is opposite the medium one. So there's a relationship between the angles and the sides. Bigger angles beget bigger sides. Smaller angles beget smaller sides. Okay, what if I didn't want to do Pythagorean Theorem? What if I kind of really getting the hang of SOH CAH TOA? I could also solve for that missing side using SOH CAH TOA. So I could have used the 37 degrees now that I have that, or I could use the 53. If I use the 37 degrees, then what I would be looking for is the opposite angle, and I'm going to use the 11, which is the adjacent. So if I have opposite and adjacent, that's going to be tan. So the tan of 37 equals opposite, which was my y, over the adjacent. So in order to get that, I just need the product of 11 times the tan 37. And again, make sure when you do these multiplications, when you have an open paren, you close it so that you don't multiply too much. Okay, so I got 8.3 that way as well. So you can get a missing side either by using SOH CAH TOA or Pythagorean Theorem when you have a right angle. The only way you're going to get a missing angle is to go ahead and use your SOH CAH TOA and then use inverse trig. Once you find one missing angle in a right angle, just use subtraction from 180 to get the other missing angle. So the level of difficulty that our assessments will match the problem sets. So when you look at the problem set and I ask you to solve for triangles, that's the kind of stuff I'm going to ask you to do on the tests. Okay, and I won't go beyond that. So on this worksheet, they first start out just having you find like a missing side and a missing angle, and then towards the remaining problems, they have you solve for the entire triangle, which is what we did. So when they say that, what you're going to do is you're going to find every missing angle and every missing side. Okay, so what do you think about this? Do you want to practice any more of these? You have this document. I think you may even have the key, but if you don't have the key and you are trying to check something, just email me and I will tell you what the answer should be. But I'm not totally sure if I put the key up or not. But there are lots of good practices just on the web for this stuff, and your textbook has some as well. So So what's your thought at this point? Because we've been going for like almost an hour and a half already. So do you need like a 5-minute break? Just, and then we'll finish up, and because we have 2 big topics, and that's really it. There's a dilation project in GeoGebra, but I think you'll be able to figure that out just on GeoGebra. And there is also a link in this PowerPoint, in the PDF of the PowerPoint, that will take you to a dilation type thing. The dilations are just similar shapes, so you're just doing a scale factor, and GeoGebra will do that for you. GeoGebra also has, there are videos up online for GeoGebra too on YouTube that will be pretty self-explanatory as well. But again, if you shoot me an email and say, I need to go over this, I'm happy to set up a time to do that. So what are your thoughts? We can power through the next 2 things, which I'm fine with, but if you need a break, I'm fine with that too. So what are our thoughts?
I'm good to just power through.
Okay.
I'm good too for right now.
Okay, Claire, are you okay?
Just go refill my water. You can just get started. I'll hop in, but can I just refill my
That's
water?
a good idea. Yeah, I've got water left, so I'm good. Okay, I'm just going to get out of this in the meantime and go back into the notes, which were here. Okay, so let me put, while she's getting water, I'll put some of these things away. So the good news is now you all have these fancy calculators on your phones, which is really cool. Okay. All right. So what we're going to do first is the law of sines. So law of sines, you're going to use that to solve for a triangle when the triangle is not a right triangle. Now, you can use this for right triangles as well, but people tend to use the whole SOH CAH TOA and Pythagorean Theorem for right triangles. It's just a little bit easier. And they tend to use, and you have to use law of sines and law of cosines to solve a triangle when it's not right. Okay, so the whole idea about law of sines, this works for all triangles if you have a pair. So by a pair, I mean you have to have an angle and a side that are paired in order to use it. So an example of when you can use it, because I was playing around with this, what if I told you that this angle was 20, this angle was 50, and this side was 10. So I'm missing another angle and another side. So I'm going to use, what I see I have a pair. I have 20 and I have the side opposite it. The second I have a pair, that is law of sines. So always look for law of sines because it's easier. It's a less complicated formula. And you want to always, just go for that first. When I ask you to do this, I will give you this formula. I'm not going to have you memorize law of sines or law of cosines. You do have to know SOH CAH TOA and you have to know the Pythagorean theorem. But these other law of sines, law of cosines, I will give you the formula somewhere. So let's see if we can solve this triangle because that's what this is all about, solving the triangles. So if I have this situation, I'm going to set up 2 pairs. So this is how I'm going to do it. I'm going to say sine of 20 over 10, okay, that's my pairing, is going to equal the sine of 50 over little c. Little c is the side that's missing. So you have a situation where you have fraction equal to fraction. So you're going to do your cross products. So 10 times the sine of 50 equals C times the sine of 20. Your desire is to get C isolated, divide. Okay, so this is a good time to use that alpha y equals so that you can get your fraction. I would highly recommend you do that. So if I go alpha y equals and I hit enter, I get my fraction over number bar number, and that's what I want. So I'm going to say 10 times the sine of 50, close my parens, and then over the sine of 20, close my parens. And I get 22.4. So we're going to be rounded to the nearest tenth. So let me change my pen color. So in red, I will solve for or indicate what we just found. So we found 22.4. So we're still missing a side. Once you start using law of sines, don't switch. Stick with law of sines. Okay. I also need to find all the angles, but look, I have 2 of the 3. So let's find the missing angle since it's right there. So you would say 180 minus 20 minus 50, and that gives me 110, which is what I need for this missing angle. Now I just need the missing side. What I'm going to do is I'm going to say, okay, I need my pairings again. Usually I tell the kids, go with, let me not do that in red, go with the values they gave you, not with the ones that you find, just in case you have an error. So they had given me the 20 and the 10. I'm going to use that for my base ratio. That's going to equal, I'm looking for B, so I'm going to use the sine of 110 over little side b. Okay, so I'm going to do cross products again. So b times the sine of 20 equals 10 times the sine of 110. So therefore b is going to be 10 times the sine of 110 over 20. So I have 10. So I'm going to use my fraction again, alpha y equals, get my fraction, and I'm going to have 10 times the sine of 110. And then in my denominator, I'm going to have 20. And I'm going to hit enter. And I did something wrong. What did I just do?
I think it's supposed to be sine 20 on the bottom.
Oh, yes. Thank you. Thank you. Thank you. I did not copy that correctly. Yep. Perfect. Okay. Alpha y equals, try that again. 10 times the sine of 110 divided by the sine of 20. That's going to be much better. Okay, so 27.5. So this is 27.5. Let me do that in red so we can see that it's a new value. 27.5. Okay, so now we have solved for the entire triangle using law of sines. So the key thing is find a pair. A pair meaning an angle and its side. And look at the relationship between the angles and the sides. So the biggest angle is 110. Across from it is the biggest side. The smallest is 20. Across from it is the smallest side. So we know that our answers are reasonable, and that's a good thing to always check. So this is one way to solve for triangles, law of sines. So there's one other way, and that's law of cosines. And this works for all triangles if you do not have a pair. So notice that you have rather big equations. You can use law of sines or cosines to solve for angles or sides. Okay, so in this situation, here you'd be solving for missing sides here you'd be solving for missing angles. So I wrote out one triangle for this as well. So if I have this situation, and let's say we have a 30 here, we have a 60 here, and we have a 50 here. And I need to solve for the triangle. And I want to practice using law of cosines. And let's say initially I want to solve for this x. So we're going to call that x, and we're going to call that y. Okay, so since I'm going to solve for a missing side, so I think I'm going to use my A, B's, and C's just to keep everything straight with this formula. If I'm looking for a missing side, I'm going to use these formulas. Okay, so let's say I'm looking for the missing side A. So A is the x. So let me, to be consistent, I'm going to make that a little baby a. So I'm looking for A. So here's my setup. I'm going to use the third one down. I'm going to say A squared equals. Okay, so let's call, this is B squared over here. So 50 squared plus, then I need to have C squared. Okay, that's what I'm missing. Okay, so hold on, I need to have another value. So what did I do? 18 and 10 and 40. 18, 10, and 40. That's what I did. Okay, so let me, can I just scratch this for a second? Because I started out this way and then I changed it, and this works better. So if I have this triangle, it's not a right triangle, but I had A, B, C, and this was 18, and this was 10, and this was 40. Now I have what I need. So I want to find little side C. So I'm going to write that up here. So little side C is going to equal A squared, which is 18 squared, plus B squared, which is 10 squared, and then minus 2 times 18 times 10 times the cosine of big C. That's what's going to go in my calculator. And it's usually best to put this in as one step. So since you really want C and not C squared, I'm going to say second square root, and then I'm going to say 18 squared plus 10 squared minus 2 times 18 times 10 times the cosine of 40. And that's all under that square root. And the reason why I'm doing that is because when I hit my enter, that is my answer. I'm not then trying to copy that down and then do premature rounding. So I'm getting C equals 12.2. So this is now, we'll change color. This is 12.2 that I got by doing law of cosines. So then you can then find one of the angles. I need to find one more angle. Once I find the angle, then I can just do subtraction and find the missing angle. So what if I want to find angle B? So what I would do is I would set up the fact that cosine of B, so we'll do this in blue, cosine of B equals, so my A side is 18 squared plus my C side is what I just found, which is 12.2 squared, minus my B side, which is 10 squared, all over 2 times A, which is 18, times C, which is 12.2. So this one you definitely want to do with your fraction. So when really what you want to do is say second cosine and then say alpha y equals. Now you're getting your fraction. So I want the cosine of 18 squared plus 22.2 squared minus 10 squared in the numerator over 2 times 18 times 12.2. If I have some error somewhere, so let me see what happened there. Go to, okay. Okay, it didn't like me doing it that way, so let me figure out how they want me to put this in clear. Okay, so let me do it this way. So I'm just going to do my fraction. So I'm going to just try to do the fraction, and then I will use my second enter key to get it. So this is 18 squared, 12.2 squared, minus 10 squared, all over 2 times 18 times 12.2. Okay, what does that equal? Okay, so that equals 0.8489. So second cosine -1 of that answer, and I get 31.9 degrees. So this missing angle that I just solved for B is 31.9, and then I would just say 180 minus 40 minus 31.9 gives me my missing angle of 108.1 degrees. And that makes sense because the 18 is the largest side. So that's it. So what I did was I also put law of sines and law of cosines maze. So let me show you how that works. Can I get out of this for a second? Do you have what you need written down before I get out? Okay. All right. So let me come back out of here. And hopefully I have that here. Yes. Okay. So I gave you the maze, but I also gave you the answers. So this is how the maze works. Here's your first problem. You start there. If, for example, you think your answer to X is 21.6, then you would go this way. And then you follow the maze. So it will give you a chance to practice. So remember, when you have a pair, here's your pair, I'm going to do law of sines there. Okay, when you don't have a pair, so this bottom one right here, I don't have a pair, so that's going to be law of cosines, and I'm going to have to do that. You don't have to solve for the whole triangle to do this. You just have to solve for the missing side, and I believe they are all missing sides. No, one's an angle. So you've got some angles and sides. But then what I did, I gave you the answer key, so you can double check yourself. So you can practice as little or as much as you want. The shaded numbers are the correct answers, and it'll take you through the whole maze. Okay, so that's pretty much the whole chapter. The only thing I didn't touch upon is the dilations, but there's other information in there about how to find out about dilations. Let me just show you the rest of the notes. So then this was the area and the perimeter. We said that the perimeter is in the same ratio as the scale factor, but the area is going to be the squared ratio. Then this is the dilations, and you can see it's just a scale factor. I give you a video link here, and there's also math bits for that. So you can watch either of those. If you need help with the GeoGebra project, even after doing that, just let me know. And then this is the last thing they said about scale factor. Since volume is a cubic feature, the proportionality is going to be cubed between two similar shapes. And since area is a squared feature, the proportionality would be squared. And that is it. You have survived chapter 3. So this would be a lot more fun in person, but thank goodness we have this technology. I think it'd be a lot harder if we didn't have Zoom and I just had to only post videos and then you were constantly on your own doing it. So this is a little bit better than just having a video class. But so that's it. So tell me, do you have any questions? Is there something else you want to go over or that you may be uncertain about? It's kind of a lot of information coming at you, most of which you've probably seen at some point, but no time recently. So I'll always give you these formulas. So when trying to solve a non-right triangle, always look for the pair. If you have a pair, start going through law of sines. If you don't, set up law of cosines. Whenever you want an angle, you're going to have to do inverse trig. Whenever you want a side for these, you'll be taking the square root because that's how these sides are related. And then SOH CAH TOA is your friend, especially if you write it the way I write it. And always remember that you're thinking of things from the angle's perspective. As you change the orientation of the triangles, it's a good idea to draw a line from the right angle to the hypotenuse so that if it's twisted in an unusual fashion, you can still spot the hypotenuse. But that's how you start out, is from the angle's perspective. That's how you figure out if you're going to do sine, cosine, or tan. I don't think I ever do anything with cosecant, secant, or cotan. So a good way to know if you know enough information is look at the problem set. If the problem set is something you can do, then you know enough. If not, see if you can figure out what you don't know with the problem set. And if you can do it on your own, great. If not, don't hesitate to contact me and I'll help you with whatever it is, okay? Because you now know all the material on that problem set and you know all the material on the first test. So you can kind of test yourself by going through the problem set. Okay, what do I know? What do I need to work on? And then you should be good. Okay, so today was the reflection paper, right? That was due today. And let me just see what my syllabus, here it is. And so then what's coming up down the pike. So class 4 will be the video. And it'll be on rigid motions and symmetry. So it's kind of not too terrible a topic. The test will be the following week. So that means that the problem set is due class 4. So next class, the problem set's due. And that's because I want to give it back to you so that you have good feedback and you know exactly what you want to go over. Okay, so if you find that you're having difficulty doing the problem set, either contact each other or contact me and I can help you with that. The problem set will be on chapters 1 to 3 only, and that's what your test will be on as well. With this new Brightspace system, I haven't figured out how to post a test now and then have it open at a certain time. So what I will do is I will just go in on February 24th and I'll post the test at the time of our class. But I'll send you a message about that. And that's how, and then you can just put it right back up. So if you want to, print it and then do it and then scan it back in, that's good. If you want to, I don't know if you have access to an iPad. I tend to do my things on Notability sometimes, but you just would scan it just the same way you do in your papers and stuff. So any questions I can answer about anything? Because there's a GeoGebra assignment that's on dilations that's due beginning of class 5 as well. And that's when the appreciation papers due. So just, you know,
Can I,
yeah,
sorry, I was going to say, can I ask a question about the GeoGebra assignment?
yes.
So I started to work on it, and I just wanted to make sure that I wasn't messing up the question. Of course, now I don't have it downloaded right here. So I was looking at the first one, and it asked to draw, I think it was a hexagon, but it only gave 5 points to label, and then said to like label E as the center point that you're creating the dilation off of.
So
And I
that's-
just,
you call that a pentagon, huh?
so I made a hexagon and I just labeled it differently. Is that okay?
You can use the 5. Yeah, why did I do that? Why did I say? Yeah, why don't we just make that a pentagon? If you've done a hexagon and you're happy with it, leave it be.
Okay.
Okay.
And then the center point would be labeled A, B, C, D, E, F.
Right.
Okay.
Right. Yep. F. Yep. Yeah, and I put the example of the quadrilateral. So as I said, you know, if you want whatever shape you want to do, don't do the quadrilateral, but you know, definitely do either a pentagon or a hexagon. And the key thing is, so let's see.
So point E is going to be this, like at the origin, not part of the pentagon.
That's right. So you want to model after this. So I probably need to reword this. So sketch a pentagon. Place point. Yeah, you don't want to have the pentagon at that origin. You want to have an extra point there so that you can then sketch from there. Because when you look at the dilation, they kind of walk you through it. If you hover over it, it tells you what you should do. Because you are going to center from the origin. So what basically is happening, if you look at this GeoGebra assignment, the quadrilateral that's in the center is the starting one. Then you make one bigger and one smaller. So you're using a scale factor of 2 to make it bigger and a scale factor of 1/2 to make it smaller. So that's how we have 3 in a row. And they are centered off the origin. So see if you can make sense of that, and I will work on the wording of that. And then I give you another place. I think that's the only one that I've made that mistake with the letters. I give you another place to put your starting point. And I have you label it F for the second example. And then you're going to sketch a quadrilateral, and you're going to just follow along. You'll have a basic one, and then I ask you to do certain things to it. The GeoGebra is pretty user-friendly. So I think just playing around with it, it'll be okay. Then you have similar right triangles. Yeah, so you're going to make similar triangles there. And then were you all okay with the parallel lines and all the different components that are equal? Because those are nice to know about. They get used a lot in geometry, and there's a lot of good activities you can do with that. Because there's an example of that in here as well. And then, a word about circles. I have you do circles here in the GeoGebra, but you'll notice that on the problem set, there's no circles. So that means that there's no circles on the test. Okay. And then the last one is lines as well. They're parallel lines with right angles. Yeah, so play around with that. If as you're playing with it, you have more questions, just seek me out. So what I wanted to say was sketch a pentagon. Yeah, I think if you say sketch a pentagon, A, B, C, D, E, then place point F, right? At 0, 0. I think that's probably what I wanted to say. So what I can do is I can change that wording and I'll repost it so that you have a clean copy. Okay, so those are good questions, Claire. So anything else for the good of the cause? Look over the problem set, see what you think. If you need more support with any of this material, let me know. You've got, references that I gave you, but you can Google a lot of things also, but the math bits are good. You've got these problem sets. I think I also posted some answer keys with the problem sets. So you should be able to kind of, take it slow and figure out what pieces you may be unclear about, and then figure out if you need to contact me or whether you can look at the material and figure it out. Either way is fine with me. Okie doke.
Just one quick question for the problem set where it does tell us to draw the triangle. Do we need to use a compass there, or can we just sketch it and label it
Just
correctly?
sketch it and label it.
Okay, so the angles don't have to be precise, right?
No.
Okay.
Yeah, when I did this class in person, I would bring in all that stuff so we can play around with it. But you don't have to do that at this point. Okay. So anything else? It's almost 7:30. So I guess it's going to be about 2 hours each time because these chapters are huge, and that's just the way life is, I guess. But at least you have me, whether that's good or bad, I don't know. But I can answer questions as it go, as opposed to when it's a video weekend. Then you may want to. You can even collect your questions and ask me in an email or ask me to Zoom with you, and that's fine. Yeah, I try to make my videos as clear as possible, but it's hard because everyone has a different background, and I don't want to over explain or under explain. It's kind of hard hitting that sweet spot. So don't feel badly if you have to ask me for more explanation. That's perfectly normal. So I think I will stop this. I'm going to stop sharing, and let's just make sure. Yeah, so it's recorded nicely, so that's great. So I think I'll stop recording now, and then I'll send the recording to the 2 other ladies who are doing other different things tonight. So let me do that. So I'm going to stop this.